What's up, everybody? So today we're going to continue on our investigation of light, what it is, where it comes from. We're going to look at this idea of light emission. Where is it that light comes from? Right? We spent the last couple of days looking at what color is, what light is, how we determine different colors, things of those sorts. But we really haven't talked about where it comes from. Right? We've talked that, yeah, it's a photon, it's moving through space, and we've got that electromagnetic radiation, but where does it originate from? Where does it come from? Well, that's kind of our discussion today. So before we get into the emission of light, we need to do a little bit of review from chemistry. So when you look at an atom, okay, we have different parts of it, right? We've got the nucleus in the middle. Okay, so we've got the nucleus right here in the middle. And as we go around the outside of it, we're going to realize that there are these orbits for the electrons, and there are different energy levels that we associate with each of those energy levels, right? So you've got like the first shell, the second shell, so on and so forth. And each of those electrons in each of those shells has a certain amount of energy that's associated with it, right? So if we've got two electrons in the lowest energy level, we go out and say we've got three electrons in the next, and we don't have any in the last one. So say we've just got, what, 1, 2, 3, 4. We've got 5 electrons in this particular atom. Okay, so with light, where it comes from is if we have some sort of energy that comes in and interacts with this atom, we can say that, okay, as we add energy into it, sometimes these electrons will bounce up to another energy level, right? So say this one's got a certain amount of energy here, I add energy into this, and it jumps up to the next energy level out here. Now, what does that look like? Well, if you think about like the lights that are on in the classroom, there's an electrical current that flows through those light bulbs. That electricity is that energy. Okay, so as that energy goes through all of the little atoms that are inside of that light bulb, they excite those atoms, and this is where we get that excited state of that atom. Okay, so if we start there and we start progressing through, we can see now that this electron, as it moves up to a higher energy spot, where it doesn't like to be there. It feels uncomfortable. It feels unstable. This electron essentially has wandered off, and it's afraid because it's not home. It wants to go home. And so what it'll do is we've got that energy that's come in, it's excited it, move the electron out. The electron says, I don't like being here. I want to go back home. And so it'll bounce back to its original energy state. So as we added energy in and it moved down, when it goes back, it has to get rid of that energy, right? Because the energy was there because it went to a higher energy spot, right? And so as it moves back up, it's going to emit a certain amount of energy. And that energy that we say that it emits, we call it a photon. And that is the energy, that is the release of light. Okay, so this, very simply, that's where light comes from. It is taking an atom, exciting it, have it being unstable, wanting to go back to its stable form, and it de-excites, releasing that energy that we call a photon, that we have as our interaction with our eye, light. Okay? So, if we look at different elements, we look at different things that are out there, we notice that those electrons are in different spots, right? They're in different shells. And so as they go from one energy level to the next, or one shell to the next, and they bounce back, there's different amounts of energy that's associated with that, correct? And so if there's different amounts of energy that are associated with that, it's going to release different amounts of energy. And if we think about what light is and how we talked about different frequencies of light, as it emits different frequencies, those will be the different colors that we see. So if you've ever taken something and burnt it, And maybe you watch fireworks, right? Fireworks, they might explode, and as they burn different colors. Those different colors that you're seeing are the different colors of light that are being emitted after they are excited, right? You add fire to something, that is energy, it excites it, and as it goes back to its stable state, it emits that light into different directions. Okay? So you might have one molecule of some substance that when it burns, it emits, a green color. Another one might emit a color that looks like blue. Another one might be red. It is all because of the different electrons in the different shells being excited and de-excited in different energy levels, emitting different amounts of energy. And this is really cool because this is one of the ways that we can look into the space and be like, hey, that star that is light years away, that we will never, ever be able to get anywhere near, we can look at it and understand what it's made of, right? We can take a telescope, look at our sun, and we can tell you what it's made of, right? We can't actually go there and take a sample and be like, oh yeah, it's got all of this in it, because it's too far away and it's way too hot, right? But we can determine what it's made of because we've gone through and we've made all these experiments. We've taken all these different elements and we burn them, and we can put a prism in front of us and we can see the spectrum as they start branching out, right? So what we can do is, if this element, it emits a certain amount of light, we have that go through a special device that divides that light into the different frequencies, and so if I've got this and it divides it up, we'll start seeing different lines on that spectrum, right? From red all the way to violet. It's going to give very specific frequencies of light that it emits. And because we know, carbon, when it burns, it looks like this. When you have hydrogen, when it burns, it looks like that. So on and so forth. So we can do the same thing. If we can have a telescope looking at a star, and we can have that light come in, diffract, this is the term that we use for breaking that apart. We diffract that light, and it has a certain color code, essentially. That's what this is. It's a code telling us what frequencies of light it's emitting. We can match that up with what we know, and we can determine what is that material that's being burnt in that star light years away. Okay? So we can take the light that's being produced by something to determine what materials it's made out of. Now, here's a really, really cool thing. If you guys have ever heard of stories where it's like, hey, we found a planet that's light years away, and we know that there is water in its atmosphere. You might be like, how do you know that? Again, it's light years away. We can't go there and take a sample. Well, what we can do is, just as we have something that burns, it will produce those specific frequencies of light, and we can match that up. We can do just the opposite. So if we've got a star out there, and there's a planet right in front of it, we can measure all of the light that's coming from the star, and that tiny, tiny little dot, that planet that's right in front of the sun, right? So if we've got a star out there, and there's this tiny little dot of a planet between us and the star, we can measure all of this, and we can get what colors are available here. And if we measure the light right in the center there, right where that planet is, the same colors, like if I took oxygen and I burnt it, and it gave me a code that looked like this, but then I also took white light and shined it through that oxygen will absorb the exact same frequencies of light. And so because of that, when that light comes through the atmosphere of that planet, and we focus our attention right there at that planet, that tiny little dot, right? Because we've got telescopes that are insanely powerful that can do that. If we look at that tiny speck and we look at what frequencies have been absorbed, we can also tell what materials are there. We can find out what gases that atmosphere is made out of by seeing what color spectrum, what frequencies of light are being absorbed by that. Okay? So the same footprint of when we burn something, or if we excite it with electricity or add energy into it and excite it, the same frequencies of light that are emitted are the exact same frequencies at which those particular substances will absorb if we shine light at it. Okay? So that's what light is, or we talk about what light is, and I talked about where it comes from. Let's spend just a quick moment talking about a couple of specific types of lights that we might have, and why is it that certain lights work better than others. Well, first one we're going to start off with, we kind of already talked about this concept a little bit in thermodynamics, but I want to bring that back and introduce to how that relates to this. We said that anything that has temperature, anything that is above 0 Kelvin, which is everything in the universe, will emit radiation. We talked about how radiation was a form of heat transfer, right? Well, that heat transfer, that radiation that we are talking about, is through the electromagnetic spectrum. So if we think about light, okay, if we think about light, it is part of the electromagnetic spectrum, but it's only a very thin piece of it that we can visually see. So things that are on the colder side that may not produce enough of a high energy radiation, a high enough frequency, then what's going to happen is it's going to be emitted in those radio waves, those microwaves, those infrared rays, and we're not going to be able to see it. But if something gets hot enough, the frequencies of which the radiation is being emitted will start to creep into the visible light spectrum that we can see. And this is our first type of light bulb. So if we think about a standard light bulb, an incandescent light bulb, all we're doing is we have a little piece of tungsten. Tungsten's the material that we found that works the best for this. And we run electricity through it. We excite all of the tungsten atoms inside of there. You look and there's this tiny little filament, this little tiny hair-sized strand that goes across. If we electrocute that and we excite all those atoms, they will start spewing out that electromagnetic radiation if we can get it hot enough. Which, if it's a light bulb and it's working, it's getting hot enough, and so it's starting to emit that electromagnetic radiation due to its temperature. Okay? We're exciting it, it's becoming unstable, it goes back to its stable state, and it releases all of these photons. The more electricity that we can pass through that, the brighter it's going to be. So if you look at a light bulb and it says like, oh, this is a 30-watt bulb, this is a 60-watt bulb, we are talking about the amount of electrical power that we are just rushing through that tiny piece of tungsten. And the more energy that we're going in, the brighter it's going to be, right? So if you have a 60-watt light bulb, it's going to shine brighter than a 30-watt light bulb. Okay? So that's our first one we want to talk about. The second one that we're going to talk about is fluorescence. Okay, so in the classroom right here, we have a bunch of fluorescent bulbs. Okay, so same thing. We can run through this electricity through, and it excites it and it releases off of it. But if we talk about things that are truly fluorescent, okay, when you think of things that are fluorescent, they seem to maybe appear more like glow in the dark, a little bit more of like those neon-ish colors. The way this works is if we are shining light onto something, and we are shining it with UV radiation. Okay, so again, we're taking light, but higher energy light. We shine it onto them. That is going to be the energy required to excite that stuff. It is then going to absorb that energy, and it is going to re-emit it as a lower energy, right? We can't see ultraviolet. Ultraviolet is too high for us to see. And so if we bring that down just a little bit, right? So if we put that on there, it brings it down a little bit and emits a lower energy level, right? This is where like a black light comes in. A black light is going to emit these UV rays, not quite as high of energy as like the UV rays you think of with the sun that give you like a sun's tan or whatnot, but it's a lower energy level of UV. And so that energy hits it, it absorbs into the stuff, right? So if you have a black light and you see kind of all those colors, that's what we're talking about here. And so it hits it, it absorbs it, and it re-emits in a lower energy level that is in the visible spectrum of our eyes. Okay? And then the last one I want to mention here is phosphorescence. And this one works very similarly. So the energy comes in, right? If you have like UV, things like that, these are like the glow in the dark objects. These are the things that if you shine light on them long enough, they start to get excited, but they're unlike the other ones where they immediately try and get rid of that energy. But instead what they do is they hold on to that energy and they're in a semi-stable state. And so instead of releasing all of that energy all at once, giving us that white light or variations of that, instead what they do is they hold on to it and they're a little bit unstable, but not super unstable. And so a couple of those atoms will start releasing that energy slowly over time. So that's why if you have something that's glow in the dark, it has absorbed that energy, becomes semi-stable, so that when you turn the light off, they'll slowly start restabilizing and slowly emitting those photons. And so that's where you get that glow in the dark look. Okay. All right. That's it for everything for today. So we've gone through the idea of light emission. What is the basis of where that light emission occurs? We've looked at a couple different types of light bulbs, different types of places that light can emit, and also understanding the idea of that absorption spectrum as well as the emission spectrum, this footprint for any sort of material as it becomes excited, what is it it's giving up, or as light's coming in, what are the frequencies that it's going to absorb. All right, that's it. Talk to you guys later.